All right. Thing is, this is a 5,000 level class. Okay, you can't expect me to teach you every single thing. You have a textbook that you should be following. I'm putting what chapters we are, what sections we are. It's your job to follow this. This is also a first level graduate class. You have to do some research. So when you come to my office and you ask questions, it shouldn't be, I don't know this. It's Sunday, 9 p.m. Let me email Dr. Z. Okay, do your research, look at your book. If you couldn't understand, or there was a, I don't know, something Emmy they taught you and then I'm teaching you something different, like, hey, there are two different clear cases, what's the problem? Then I'll be happy to help you, all right? So read the book, do your research. That's basically what I do. Prismatic join, and I'll show you. So you can do that. So reserve me for questions that you cannot figure out on your own. That's the third item I want to talk about. All right. Now, how many of you are actually following the book? Well, you have the link, right? So this is week 4, right? If you have noticed, which I'm sure you have, a lot. I'm talking about a lot of topics, and they seem disconnected, right? You don't quite know where we're going right now. The thing is, if you're following the book, you know that we will start robotic that will make sense to you in chapter 4. So it's 116 page into the book. So, and for the first 4 weeks of what I'm teaching you. So this 115 pages is basically teaching you the language of dealing with the first robotic arm. All right. So there are fundamentals that you need to learn. So once I say, okay, let's assign a frame. And I tell you, this is the axis, X and Y. I'm going to move on because I expect that in the first 4 weeks, you're following and you understand. So things we're talking about here, they seem simple right now, okay? I'm trying to keep the pace slower so you can catch up. This is the first time you're dealing with these things. I know some of the Emmys already, they know about some of the topics and some of the ECs, all right? And the CSE. But so don't think this is going to be the pace of the class. The pace of the class is going to be faster. All right. I'm trying to on purpose be slower. So once you know the fundamental, I feel like I don't have any more responsibility to bring everyone to the same page. So the first 4 weeks is bring everyone to the same page. Now, if you think you need help, go to your book. When I give you class participation, it doesn't mean, oh, I want to know who's in the class. Well, I do want to know who's in the class and who's actually listening. But it's also who actually looked at the lecture slide from last week or last class for 5 minutes. So when you come to the class, come prepared, please. Okay, so we don't have to follow I will try to do reviews and follow-ups, but maybe 5 minutes. Or I don't have to give this 10 minutes talk about how to prepare yourself for the classroom, all right? So a lot of class participation is to check if you know the past knowledge and if you can incorporate it in what you just learned. And you're going to use it in the future. You'll see that we're going to use asymmetric matrix that we talked about on Friday. So I expect that you remember that, or at least you're able to go to that slide of that lecture and say, oh, that's how we make it. All right, make sense? So listen up when I'm talking and try to come prepared if you want to be successful. If you're here to get a C or B, then it's fine. Really. This is an elective course. If you're spending your time at 3 p.m., you know, most of us are tired by now, and you choose not to learn and just get a grade, that's your choice. I'm here to make this experience at least fun. All right. Enough talk. Let's go to axis angle example. All right. So if you remember last week, sorry if I'm yelling. I feel like I need to talk loud for you guys to hear me, even though I have a mic. I'm trying to adjust my volume. So last week we talked about 3 parameter representation of rotation, right? Do you remember what they were, the first 2?
Spoiler angles and optical.
All right. So this means that if you have a rotation matrix 3 by 3, there are 9 elements in them. This rotation matrix was created by rotating this frame, right? Now, there are 3 ways you can find out what rotation caused that rotation matrix. So it could be over angles, which is rotating about two axes, right? For example, x, y, x, or z, y, z. So the first and third axis are always the same. The second one is different. We had 6 different combination of those rotation. You could use roll, pitch, yaw. So you could use the same 3x3 matrix and find roll, pitch, yaw angles for them, which gives you 3 angles. So these are different methods of solving the same problem. Now, axis angle is the third method of solving that problem. So if this is, I try to use my little art and crafts project, so I can, yeah, everyone can see them. So if this, well, this is your coordinate frame, right? It can be attached to anything. Now, if I had a point here, right? Track this point, I'm moving this frame, this point is moving. So if I saw this point at initial time 0, now you see 10 seconds later, and if I ask, what's the rotation matrix? Oh, this is the rotation matrix. Tell me what was the rotation? One of the methods is, you know what? Draw a vector from here to this point, okay? A unit vector, so you don't care how far this thing was because you can always scale a unit vector. So this will tell you the direction. So this is the unit vector, and then you rotated this vector, you see, this much. So you find a rotation angle for that unit vector. So that's the third method of finding 3 parameter rotation. So still the same rotation matrix, different method. Now, this is more general because you are finding 2 things, one vector and one angle, right? Now you might say, okay, vector has x, y, z, and the angle is the 4. This is 4th parameter, but I'm telling you this is 3. Why? Which one is the dependent variable here? Because kx, if you remember, we said this k is kx, ky, kz, right? So if there's 3 elements there, and there's also a theta, that's 4 parameter. But this is a 3 parameter solution. So one of them must be dependent on the others. Which one is it? No, you need to know theta. So if it's not theta, it must be the vector, right? Something in the vector. Can you try to figure that out? What about the vector? That you only need 2 of them? Did we say this vector was unity vector? So if the length is 1 and you have 2 of the components, you have the 3rd one. So this is still a 3 parameter problem. Okay? So that's why we're only like, when you see that, I'm just saying alpha and beta, I don't even care about the 3rd angle, wherever it is. Because when you're in the space, when you're in the plane, like if you know the combination of the addition of all of your angles, right? They are orthogonal in your frames. So if you move theta and another like phi, you kind of know the 3rd angle. So we are working with our minimum, with the minimum requirement. Now, how do we relate our rotation matrix that we have to this method? So this RK and theta is the rotation matrix you can write for any arbitrary K and theta. Now, how did we get there? If you remember, we said that, look at this. If K is there, if this was if we assume at the beginning, this was our vector we defined, this is another frame. What if I put another frame that this is the Z frame of that? So when I'm moving, this other frame is moving too. So if I can find the rotation between these 2 frames, it's like I found the rotation of this vector. If this is the Z frame, you see that the Z frame is not moving. Everything is rotating around it. So there are 2 other rotations that happens here, right? Around x-axis and y-axis. That's why we have 2 angles. Now, let's say rotation from this original frame to our new frame, that wherever this vector is going to be RZ alpha and RY and beta, right? Alpha, beta, arbitrary, depending on where this goes. Now, we know from similarity matrix that if you have 2 frames, you have a rotation matrix in one, you have that same rotation matrix in the perspective of the other reference frame. So I can say, so one of the matrices is RK theta, what I'm trying to find, and I'm saying that I, on purpose, put a Z1 on my vector to see where it will rotate. I'm gonna say my other one is RZ1 theta, because theta is the same for both of them, right? So can I write a similarity matrix to connect these two together? So RK theta is going to be R01 inverse RZ1, which is my frame that I put on that vector, and it rotated theta, and R01. Now we have R01 here from here, right? So we can write the inverse. And we know rotation around z-axis is cosine, negative sine, sine, cosine, 0, 0, 1, 0, 0. So we already have this one in the middle. You don't know what theta is, but it's totally fine. So if you now multiply all of these together, you will get this guy. So I saved you the time of proving that. It's going to be this. V of theta is basically 1 minus cosine of theta. You'll see that there. Now, dealing with this directly, if I have a 3 by 3 matrix with numbers, every of these elements are equal to the counterpart in this matrix. Now, if you solve these equations to find two variables, theta and k, you'll get this too. So it is solved. You don't have to solve anything. It's already solved for you. So if you have a rotation matrix and you want to find axis angle representation, all you have to do is to find the theta and the k. The theta is from trace of that rotation matrix minus 1 divided by 2 cosine inverse. And then k, the element of k follows this. It depends on the theta and this relationship. How did you get this? Solve that. 9 equations for 2 variables. Some of them are dependent on each other. All right? Yes.
What was the 0 3 by 3 matrix?
Which one?
The 0, 0, 0s, the 3 by 3 matrix. What was that?
Rotation around Z. Is that this one? That's what we're talking about?
You wrote. 3 by
Oh,
3
this is not 0, 0. This is some numbers. Numbers. This was like a block. Okay, so every element corresponds to this big matrix. All right. Now, if I give you a 3 by 3 matrix with numbers and I ask you to find the representation of axis angle, you should be able to do that. Okay, so we have two things here. I could give you few rotations that happen one after each other and ask you what is the rotation matrix representation, 3 by 3 matrix. I could go backward. I could give you the 3 by 3 matrix and ask if you can find what kind of rotation resulted in that. For this backward, you have 3 ways to do it. Euler, Fish-Roll, yaw, or this one. Okay, so feel free to use any of them, but if I ask you to specific things, you have to use that. Now, your next example that you're supposed to maybe take a look at. So I gave you 3 rotations, okay? You have the angle. This will give you a rotation matrix. I want you to find the axis angle representation of this rotation. Yes. Oh, oh my God, such a lazy person. Yes, because I was going to copy and be lazy. So followed by a rotation of, so generated by rotation of 90 degrees about Z, 0. These are the things I needed to add. Thank you. Followed by rotation of 30 degrees about Y0, and followed by rotation of 60 degrees by X0, all happen in current frame. So you have R, Z0 and 90, then you have R Y0 and 30 degrees, then you have R X0 and 60 degrees. Yeah, these are all in current. So basically, I'm asking you to find R, K, and theta that represent this rotation. Also, I could just. Question.
Y0, 33 is about Y0.
Or x0. These are all degrees, and the first one is 90 degrees as well. One of them is 30. 30. Oh, no, this is X, this is Y, this is Z. Just look at this. This is the first rotation, this is the second. This is the third. Where? This one?
Is it post multiplication or pre multiplication?
I don't know, you tell me.
I think it's post. Right.
So, yeah.
Doesn't it start?
Oh, that's what you mean, okay. Yeah. Caught the teacher. Thank you, Derek, though. The thing is, you have to be able to communicate properly. Otherwise, I would be here in half an hour. I wouldn't understand what you mean. Done, but you were right. So, because this current frame is post multiplication, right? So the first one is R 0 and 90. Then R y0 and 30, and r x0 and 60. Okay. Now I'm not gonna write that because I was deleted. You write it. I will give you the solution. Which also the solution might be wrong, but well, you assume this is the multiplication. And I will leave it to you to prove I'm wrong. Okay, let's say this is right. It's obviously messed up. Let's say you have your 3 by 3 matrix. All right, now how do we find theta and k? What's the trace of this matrix? Matrix 0. How do we know? This is the trace. 0 plus negative square root of 3 over 4 plus square root of 3 over 4 going to be 0. So cosine inverse of trace of r minus 1 divided by 2. This is going to be cosine inverse of negative 1 over 2. What's the angle here? Huh? 120.
Oh, yeah.
Yeah. You meant pi over 6.
Oh, no.
Try to save you. All right, so we have theta. K is 1 over 2 sine of that theta. Then you have to follow this to create. So 1 over square root of 3. Then this element is 1 over 2 square root of 3 minus 1 half. Then 1 over 2 square root of 3 plus 1 half. So then you will get your k, which this would be your kx, ky, kz. So we started from 3 rotation, about 3 axes, right? You represented that rotation with a different method, theta and k, axis angle. Does that make sense? I'll let you write this, and you don't have to actually write this because it's in the annotated version, but if you want to have it in your notes, you can. But okay, I'll let you write because nobody's looking at me right now. The point is, you started from 3 consecutive rotations, right? Around different axes. Could be the Rokuchiya situation, right? You found the matrix representation of that rotation. Then you all again converted that to axis angle representation. So if you look at the big picture, a 3-axis rotation was converted to axis angle rotation, which both share the same rotation matrix. Good. All right. It is in the annotated version that are already posted, so you should actually have access to it. Trace of R. Yeah, it's the, you can add the element, the diagonal element, that will be trace of your matrix. Yeah. All right. So this is the end of lecture last week. All right. Hopefully the whole rotation thing makes more sense now, and why we have 3 methods. They should all be equivalent for finding that rotation matrix. You can represent how to get to that rotation matrix differently. All right. Any questions on this course? No? Okay. All right. So today there is no class participation. your participation is to review the stuff that I talked to you from now on, within the class for half an hour, and you're gonna solve practice problem on Wednesday of things that I'm saying here. Okay. All right, so if you remember a rigid body configuration, we talked about it, we said that a rigid body has an orientation, okay, and we can also define a position for it. So position, X, Y, Z direction, and orientation is the rotation around the three principal axes, following the right-hand rule, all right? Meaning that in right-hand rule, if you know where Z is, you know where X and Y are. If you don't remember, go back to the lecture that has a hand on it. But if this is the yellow is your Z and pointing up, when you close this, X always closes to Z. That's the positive direction, all right, counterclockwise. So you only need one axis to figure out the other two, all right? Usually in robotic, we will give you the Z axis, which is the rotation of any joint, if you had a revolute joint, or translation of your prismatic joint, all right? So for any rigid body, that was just a reminder, for any rigid body, we could have three orientation and three element per position. Now, if you start from frame 0, frame S, your fixed frame, and you move somewhere, you're gonna have a position, right? You're gonna also call it translation. And then you have this rotation. So here you have rotation, right? Sorry, this is your rotation or matrix. You already know what rotation matrix is. And if you have two frames, you're able to write the rotation matrix for between the two frames, correct? And if I give you the position of this point, the origin of one frame and position of this one, you can find their distance. Now, had you, like, what is the reference point for that distance? What's your frame of reference? Well, you ask me, where do you want me to measure that from? You want me to measure point P from S frame or P frame? Then I'll tell you, okay, do that. I will tell you which one, all right? So for position, you need to know what is the reference frame that you're measuring. Combination of these two is called transformation. Or if you remember from math, it's also called mapping, all right? So we are gonna combine these two together. So we have a 3x3 matrix for rotation and 3x1 matrix for position. We are gonna combine these two, but it's gonna give us some trouble when we're doing the matrix multiplication. So we're gonna augment it to a new form. We're gonna create a 4x4 matrix that represents both things inside of it, all right? So we're gonna call that homogeneous transformation. So your homogeneous transformation is the special Euclidean group, SE3, okay, that contains a rotation matrix from R3, 3x3 matrix, plus a translation from R3, X, Y, Z, 3 elements. Can you wake him up? You really need to listen to this, okay? This is the base of next class. Now, this transformation matrix, you hear, sometimes you will see it represented as T or H. T for transformation, H for homogeneous transformation, all right? Really, the naming convention doesn't matter. We say that T is equal to R and P, rotation and position, and this is the form. So T is R and 0, so now 0 is basically a 3x1 vector of zeros. And position, P1, P2, P3 is X, Y, and Z. And the last element is 1. This is how we augment it. So now this is 4x4. And we can now perform matrix multiplication. So we will just multiply 4x4. And when we finish our multiplication, we have a 4x4 matrix, which we know this, I call it first top 3. I mean, this 9 element will always be rotation. And then these 3 elements will always be your position. Yes.
Are R32 and R33?
Yes. All right. So if I give you two frames, and I give you what is the direction of each of x, y, z, and you know what is the distance between one origin to another, you should be able to create a homogeneous transformation between the two frames, right? All right, you're gonna prove yourself. Okay, so you see that we augmented our position as we added one. We will remove this one whenever we are introducing the point. So let's say that there's a point transform, and then you do matrix multiplication, you get a matrix that's 4 by 1. If I ask you what's the position of this point now, if this was P2, you're trying to find, let's say P star. You're trying to find P star, and you will get to something like this. All right. What would be the actual position of your P star? If you want to tell me the coordinate of that. You take back one, you cut it off, right? We just put one there as a placeholder to augment to our 3 by 3 matrix, right? Now, if they all happen to be one, don't get confused. This is always one. Doesn't matter what the other ones are. All right. Now, a couple of properties or prepositions for homogeneous transformation. Yes. So we use that one here to augment. So we are adding zeros for a rotation matrix. This is when you multiply. So the 3 x, y, z of position will get multiplied because that's the last column, right? But so we put these as 0, and then you augment this as 1, as always like that. So you already know your last row, 0, 0, 0, and 1. And that's for augmentation. So don't worry about it. I won't go into the math part of it. If you're interested, you can search or also look at your book to see how that happened. All right, prepositions. Do you remember what was the inverse of a rotation matrix? How do you find quickly the inverse of a rotation matrix? Yusuf, you remember? What is, R inverse is equal to R transpose, right? For transformation matrix is not. So for homogeneous transformation, T inverse is not T transpose. Okay, T inverse is, again, it has to be a 4 by 4 matrix. The last row is 0 and 1. Okay, we will find the inverse of rotation matrix is transpose. So it's R transpose. But to transpose that point, the position will be negative R transpose T. So if you want to find the inverse of a transformation, this is how you will find it. What does it mean? I went from this position, okay, I transposed here, like I translated and then rotated. The inverse means, how do I go back from here back to where I was? This is the inverse transformation. So this was the transformation. This is the inverse going back. Sometimes you have to go backward. And that's where you use the transformation. Follow this form. So if you have a transformation, you already have the inverse, right? It's just a little bit of math into it to find it. For all the homework and exams, everything, you have to follow this notation, this formula. You can't just plug in a math library calculator or find the transpose of 4 by 4 matrix, because that's not meaningful. All right. Now, the other proposition is the product of two transformations is also transformation. So the first will apply to the new transformation. All right. So if I'm going from one frame to another and another, I could go directly to that third frame. If I multiply the two transformations, you will see examples about that. The third one is that so the transformation matrix is associative, but it might not always be commutative. So assume it's not. In some cases, it might be, depending on. All right, but we're assuming that it is not. So T1, T2 is not equal to T2, T1. All right. So you need to remember these and have these handy when you are solving, at least for next week, next Wednesday, solving the problems. All right. Okay, so now I'm gonna show you like how to go from one frame to another, and then we solve one problem. So hopefully we can finish on time. Any questions so far? Pretty straightforward, basics that you already knew, or not hard to grasp, right? You should be able to remember. Now, we'll see that we have 3 frames, A, B, C. I always talk about camera and robot, right? So now this is an example. So let's say there was a frame attached to your camera, a frame, so you see a camera, and a frame connected to this robot, and a frame connected to that robot that's moving, right? So we want to know the relationship so we can measure, see the same point or same transformation from each of these different angles. Now, how do we go about moving from one frame to another? Assuming we will have rotation and we will have translation. So 4x4 matrix, homogeneous transformation. We can say that if this is frame A, I'm going from A to B. So I'm showing my homogeneous transformation with that arrow. I can say TAB with subscription from the previous frame to the new frame, following the same convention as rotation matrix. All right. Now, if I go from here to here, what would be my homogeneous transformation? TBC. John, what would this be? TCA. All right. So now if I have a rotation between these two, RAB, and if I have the position of the two coordinate frame, I'm measuring with respect to, let's say, A. If I have this, or if I have any point in frame B, okay, then I can write this transformation for it. So you can say TAB, moving from frame A, I'm going to frame B, and then I'm going from B to C. So if you look at it distance-wise, I went from here to here, right? This is how I traveled. This two, I could have traveled the other way too, right? So these two are actually the same. So their transformation will be the same. So I move between two, TAB, TBC. I can use the trick of canceling subscription, and this gives me TAC. Okay, yes.
I think TAC is equal to TCA.
You tell me.
Do
you remember the propositions? Yeah, so we said proposition first. So it's not the same. You're going backwards. So you have to use that matrix that we showed to find the backward motion. So it looks the same, but the direction is backwards. So your theta is negative theta. Your x is negative x direction. So it has to represent in your matrix. So good question. So you will follow this transcription, right? The subscription cancellation. So you find TAC. Now, what if I wanted TCA? I'll go here and say, you know what? I'm going to find this. I already know R. This is the first 3x3 element. I already know 3x1 for position. I use those two to create this one. All right. Now, let's do this. Let's practice on this one. Start from frame A. All right. Start from frame A. Move to each frame. Write the transformation matrix. Come back to frame A and tell me what is the final transformation. Start from A, walk through all frames, go back, and in frame A, and in frame A. What is your T? So why are you not doing that? Okay. Okay. Why you're not doing the answer to this? What you find should make sense. That's what I'm trying to show you. Okay. You don't actually have to write because you don't know the directions of the axes. Just write the notation, like TAB, TBC, and see what you end up at. Like this, TAB. Then this is TBC, TCD, TBA. And then, yeah. You have it?
Yeah, starting at the time.
Yes, that's what I wanted to get there. But I wanted to write like this because you didn't, so this part is in your head, you wrote this one. So try to always write all the steps in homework, exam, because you get credit for anything that you write, and also show me your train of thought. So just writing a final solution will not get you anywhere. So let's do this together. I know some of you already done. Was that your question? Have you write it? Okay. Stay there and I will. Good though. All right. So starting from frame A, I'm gonna start walking. Here, TAB multiply by what? Multiply by. So we arrived, right? Let's cancel. These two cancel. These two cancel. These two cancel. We ended up with TAA, which also cancel, right? What did you get to? Identity matrix, right? So you started from the frame, you end up in the same frame. What is your rotation? You missed that part. Identity. What's your position? 0, 0, 1, right? So you get, so it makes sense. You expected to get this. So basically you got 1, 0, 0, 0, 1, 0, 0, 0, 1. This was the augmentation and your position is 0 because you're back to where you were. And identity rotation means you didn't rotate. Yeah, I knew what you're doing. That's why it's good to show the steps so I know what's in your head. I like to get into the head. That's pretty. All right. So, but that's not the only thing I wanted you to look at. Now, let's see, we wanted to find TAB. This part. So we know that whole thing is identity, right? If I had these three and I was trying to find TAB, what do you think I could do? So you find the three and to find the inverse would be TAB. Now, if I wanted to find TBA, you get the inverse of the inverse. So let's say the question was to find TBA, right? What is TBA? Go walk from B to A. You had TBC, TCD, and TDA. I will give you that. So you would say, okay, I will find TAB, multiply by the three thing that I have already. It will be a 4x4 matrix, right? Multiplication of these three. Following? This is identity, right? So then TAB is the inverse of this 4x4 matrix, which you can find from the proposition. Now to find TAB is TBA is TAB inverse. So you get the inverse of this, again from the proposition, and you find the final solution. Yes. No, TAB, okay. Here. So TAB is not identity. TAB, we found that TAB times TBC times TCD times TDA is identity. Now, TAB is the inverse of those three. I just was trying to be lazy, but doesn't work. Inverse, right? Now, if I'm trying to find TAB, is the inverse, well, I can't write that, okay, because you guys are gonna grill me. Copy, paste. Is the inverse of that. TBA, okay, thank you. Almost there, almost got it, nope, failed. All right. So basically playing with these transformation. Now, if you had two of them, and then you could only find the other two, but together, you couldn't find them separately, right? You have time? Maybe I want you to look at the example and I will talk about it on Wednesday, but not doing that. This example we can use. You have two frames, frame A and B. I want you to write the transformation, homogeneous transformation for this. You have two frames, you have the direction of X, Y, and Z. You can find the rotation matrix, right? This is, if this was origin here, and is origin of B, origin of A, this is that, this vector. Okay. So I'm gonna say this is a P of OA, OB. Does it make sense what this is? This distance between the two coordinate frames. You have the rotation between them, right? So I want you to find what is P in frame B, in frame A. So you have P in frame B, you have it. What is P in frame A? P is a point, is it on a car or whatever object that you want. I'm gonna call this P translation. So this is the translation between the two frames. So it's probably easier to P trans. So your P translation is 0, 3, 1. Your RAB, you need to find it. You have it, you just need to write it. And I'm asking you I'm asking you what is P in frame A. You know what P in frame B is. This is P in frame B. So if, just like rotation matrix, if you had a point in frame A to find that point frame B, you would say pre-multiply by the rotation matrix, right? Here you will say pre-multiply by the transformation matrix. Make sense? So we will solve this on Wednesday. Good. If you have any question, I can stay a little bit longer today. Otherwise, I'll see you on Wednesday.